Hello, everyone. So in this video, I wanted to talk a little bit about this section on street routing problems. This is sort of an introductory section to graph theory, which is what we'll get into in the next video. Um, However, there are some real-world kind of problems that we talk about in this section that we will sort of model using mathematical graphs in the next few sections. So I just want to talk about a few of these. One of these problems is called the security guard problem. So what is this? What is this about? This is just about um, you have some city, or really any kind of, you could imagine even a building which has aisles or some kind of map associated to it. Um, and you have a security guard. And the security guard, well, starts maybe say in one location. I don't know, I'll choose the location of the start to be over here, say. Okay. So I have some location, which I'll label as S as start. And then I have some maybe location. It could be the same place, but it could be some other location that's the endpoint. I don't know, let's say the endpoint is here. And the security guard, you want to be able to sort of walk and check every block, but the security guard doesn't want to sort of walk up and down the same block, wants to cover as much territory as he or she can. And so, they want to kind of take a walk around the neighborhood, but if they did something like this, then they're sort of back and they have to over walk their prior steps. So the goal is, given a map or given some kind of layout, can you design some route for the security guard that would minimize those sort of overlaps that would, or ideally, that would allow them to sort of cover every block once on their route. So this is one of the problems that is talked about in this introductory section, and it's sort of a practical problem that you can imagine having to solve. So another type of problem having to do with maps and sort of street routing problems is sort of this mail carrier problem. So problem number two, mail carrier problem. And it's very similar to the security guard problem, um, in that you have a starting point and an ending point. So again, let's say maybe it's the same. Again, maybe it's the post office, or maybe the mail carrier takes it, um, takes the mail truck home. So here's a start point and some end point. Put the end point here. And now, well, you may have some of the roads. Uh, well, the mail carrier wants to drop off mail, and so there may be some roads, say, see if I can find, say like here, where you need the mail carrier to go down one way and also the other way. So here I'll use there's some roads where you'll want both directions, because the mail truck kind of pulls up, and the mailman or mailwoman, mail person puts out the mail into the box. So some of the roads you want sort of to go both directions. You don't want to just go once through that neighborhood. You want to go twice. You want to go in both directions. And so again, but it's the same problem otherwise as the security guard problem, in that you want them to start in one place, kind of take a route, and not have to kind of retrace their steps unnecessarily. So you want them to only be going in one direction, and then if they have to reverse the direction along certain blocks. So this is called the mail carrier problem. A variant of that is this sort of UPS problem where only some buildings have to have deliveries that need to be made, and not all of them, you know. So then you want to, of course, omit driving around, you know, aimlessly, and not going to buildings where there's no package that needs to be delivered. So these are very real world practical problems that people can solve, and that sometimes algorithms are written um, and done with computers on how to solve these problems so that people can take the most efficient routes. Now, there's another couple of problems in this section that are more, I don't know, historical and, uh, well, interesting in some ways to me. Um, and that's one of them is called the Bridges of Königsberg problem. So this is maybe problem number 3 that was talked about in this section. And this is called the oops, Bridges of Königsberg. And Königsberg is not a city that exists anymore, but it used to be a city in Prussia. Well, actually, the city exists. It's just called something different. It's in Russia now, but it was a bustling city in its day, and uh, it had these very famous bridges. And I'll illustrate them in case you can't see. So there's a bridge here. There's a bridge here. There's a bridge here. There's a bridge here, 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 and here. So there should be 7 altogether. And yes, there are. Um, and you have this island sort of in the middle here, and then sort of a peninsula. I don't know if this is another island. I don't know, peninsula is the wrong word here, but some kind of other landmass, and then 2 land masses here and here. And the question that was asked a long time ago was a sort of a mathematical problem, is if you can start anywhere on any particular landmass, can you tour Königsberg in such a way that you visit each bridge or you cross each bridge exactly once? So let's say you were a tour guide and these bridges were very famous, and you wanted to bring customers on a walk, on a tour of all of these bridges. Can you get a route so that um, each bridge is visited only once, so that you don't take them on longer of a walk than they need? And so this problem is a famous mathematical problem. It was solved um, and in a nice fashion by a mathematician named Leonhard Euler. Not to be, I mean, so this sounds like Euler, by the way. Um, and this mathematician developed sort of the idea of graph theory to solve these types of problems, and has had a very successful um, run as a mathematical subject, and there's still many questions on this subject today. A variant of this problem, we'll get into the solutions of these problems in the next few sections, but a variant of this problem is this sort of bridges of Madison County. This is problem 4. And the idea behind this is similar. The way it's explained in the book is you're a photographer who wants to take a picture of every single one of these bridges, but you want to um, you get charged uh, exactly think what they say, $25. So you get you're charged a certain amount for crossing a bridge each time. And so the idea is you want to minimize your expenses. You don't, maybe you have to cross a bridge twice, but you want to find a route that will minimize the cost to take a picture of each and every one of the bridges. So this is another sort of street routing problem that we'll look into solving in the next few videos. All right, so this is, I know this, we didn't do any mathematics and we didn't solve any problems, but we talked a little bit about some of the problems, and that's really just the content of this section. So I just wanted to go over it with you all. In the next section, we'll develop some tools to create models that start to solve these types of problems, or at least recast them in a mathematical way. All right.